Okay, so in this video we will be doing the last topic of this chapter and midterm 1, which is the marked Poisson process or marked Poisson processes. Okay, now just like the compound Poisson process, marked Poisson process is also an extension to the general Poisson process. Okay, now in general Poisson process, what we do is, in general Poisson process, we are more interested in the arrival pattern or arrival times of something. Okay, anything like, for example, a customer entering a shop or a patient entering the hospital. Okay, so in both the shop and the hospital, these are systems. Okay, and the customer and this patient, these are the entities. Okay, entities entering into this system. Okay, and as a whole this process is called events occurring. Okay, this is an event occurring over time period t. Okay, and the events occurring over time period t, these are represented by a Poisson process. Okay, and the parameter is lambda into t, where lambda is the rate of the arrival and t is the time frame. Okay, the time interval. So this is the general Poisson process, but in the marked Poisson process we have another thing in addition to this general Poisson process. What is the other thing? Okay, besides in marked Poisson process, what we are interested in is, we are interested in the timing of events occurring, and the second thing that is additional to the general or simple Poisson process is the magnitude. Okay, the magnitude, or we can say the kind of event occurring. Okay, so for example, we take the example of these customers. Okay, now customers are entering in a superstore. Okay, now these customers are entering at the rate of lambda, okay, over the time period t. So this is a common Poisson process. But the other thing that we are interested in is the kind of service they need. Okay, this kind of service they need for individual customer is called mark. Okay, this is the mark of each customer that is entering. So we have lambda, which is the rate of the process, and we have the service that is each customer is demanding. So this service type is the mark. Okay, the other example that I can quote over here is the example of for example, what we can say, for example, the insurance claims. Okay, so claims are entering the system, claims are received by rate of lambda per unit time. Okay, but the amount of claim, the amount of each claim is the mark of it. Okay, so this is how we can differentiate between a simple Poisson process and a marked Poisson process. So marks, actually these are the additional things, okay, and these mainly refers to the magnitude or the type of event that is occurring. Okay, I hope you have understood you understood the definition or the essence of this mark thing in the marked Poisson process. Okay, so it is an extension of the normal Poisson process, but in this we are interested in the magnitude or the type of event that is occurring over the time period t. Okay, so now let's go towards the deeper towards the subject. Okay, I will now explain it using the amount of each claim is the mark of it. Okay, so this is how we can differentiate between a simple Poisson process and a marked Poisson process. So marks, actually these are the additional things, okay, and these mainly refers to the magnitude or the type of event that is occurring. Okay, I hope you have understood you understood the definition or the essence of this mark thing in the marked Poisson process. Okay, so it is an extension of the normal Poisson process, but in this we are interested in the magnitude or the type of event that is occurring over the time period t. Okay, so now let's go towards the deeper towards the subject. Okay, I will now explain it using some calculations and some examples. Okay, now let's see the mathematical perspective of it. The mathematical perspective of marked Poisson process is MPP. Okay, now here we know that the events in a Poisson process that are occurring after some time interval. Okay, we have some waiting time over here. For example, this is W1. This is the time at which the event 1 is happening over the time period t. Okay, this is the time frame and this is the overall waiting time. Okay, this is the waiting time for the first one. Here we have W2. This is the waiting time for the second event to occur. Okay, so let W1, W2 up to Wn are the event times. Okay, event times over time period t. Okay, so the overall time period is t, and W1, W2 up to Wn are actually the event times. Okay, and the events are following a Poisson process, okay, with the rate of lambda. Okay, now with each this event time, okay, with each waiting time or each event time, okay, we have a mark associated with it. Okay, let these marks be represented by y1, y2 up to yn. So with each W1, each event time, we have a mark associated. Okay, for example, customer 1 enters at W1 and he has a request for some sales. For example, he wants some audio device. Okay, so this audio device or the type of service he needs is the mark for it, and W2 is the second event, second customer entering into the system, and Y2 is the mark for it. For example, he needs a notebook, okay, and so on up to Yn. Okay, so Y1, Y2, Y3 up to Yn are the marks associated with the event time W1, W2, W3 up to Wn. Now in the marked Poisson process, okay, the collection of event time and marks is a pair, okay, as a pair like W1 Y1, this is one pair, W2 Y2, this is second pair up to Wn and Yn. This is called the marked Poisson process. We can represent it as these kind of pairs, okay, while W1 is the event time and Y1 is the marks associated. W2 is the event time and Y2 is the mark associated with that event exclusively. Okay, so this is the mathematical perspective of the marked Poisson process. Okay, I will continue into the next video, and in the next we will do the mathematical the deduction, or we can say the equation making. Okay, we will develop the equation for it. Now let's do the interpretation of the marks distribution. Okay, how they are distributed. Okay, so the interpretation is that each mark actually is identical and independent, okay, distributed. IID. Every mark is identically and independently distributed of each other. Okay, so one mark does not depend on the other mark. Okay, the other thing that we can interpret from this distribution is that the probability of having a particular mark is independent of the time of occurrence. Okay, so each mark actually, the probability of having the particular mark over the time period t is independent of the time of occurrence. So it does not depend on when it is happening. Okay, the probability is not dependent on when the mark is happening over the time period t. Okay, and the other thing is that given the total number of events, okay, which is denoted by x of t, actually the marks are distributed independently. Okay, and it follows the binomial distribution. Okay, so that is the distribution of these marks over the time period t. Okay, now we will go forward towards the equations and visualizing it. We have events occurring with 2 marks. Okay, marks 0 and 1. These are the marks. Okay, like the two types of events are occurring, okay, over the time period t. Okay, now we know that x of t is the total number of events occurring over time period t. Okay, and these are the combined events, okay, with both marks 0 and 1. Okay, so x naught of t are events with mark 0 that are occurring over time period t, and x1t are the events with mark 1. Okay, so now the probability that x naught will happen, okay, the probability for x naught of t is equal to p. Okay, so it is the probability, I must write it over here, probability for an event with mark 0. For example, we have like two type of customers coming towards a shop. Okay, one with 0 mark, and 0 marks represents that they need some food material, okay, some food, and we have one mark 1, okay, and mark 1, for example, they need beverages. Okay, so mark 0 represents the customers that need food, and mark 1 represents the customers that need some beverages like Coca-Cola or Pepsi or anything. Okay, so now we have differentiated or divided the customers into 2 marks. Okay, now the overall probability is between 0 and 1. So the probability for the processes or the events with 1 mark, actually it will be equal to 1 minus p, because p is the probability with 0 mark, or q. Okay, and we know that 1 minus p is equal to q. Okay, so the overall probability is equal to 1. The sum of all probabilities for both events occurring is 1. Okay, and p is the probability for the events with mark 0, and q or 1 minus p is the probability for the events with 1 mark 1. Okay, so these are the general instructions you must know. Okay, now we know that both of these are two independent 0 mark or q. Okay, and we know that 1 minus p is equal to q. Okay, so the overall probability is equal to 1. The sum of all probabilities for both events occurring is 1. Okay, and p is the probability for the events with mark 0, and q or 1 minus p is the probability for the events with 1 mark 1. Okay, so these are the general instructions you must know. Okay, now we know that both of these are two independent, both are independent Poisson processes. Okay, so for mark 0, it is represented by lambda into the probability of this mark 0, and for Mark 1, it is represented by a Poisson process with the lambda 1 minus p or lambda into q, because 1 minus p is equal to q. So these are the rates of these processes, and both are independent Poisson processes. Okay, now using these we can find the combined probability. Okay, condition on that the total number of events occurring is x of t. Now we know that the probability that the total number of events is equal to n is a Poisson process, and it is equal to lambda t raised to the power n e raised to the power minus lambda t divided by n factorial. This is the normal Poisson process. We know that. Now using the same, for example, the probability of having j number of events with mark 0 and k number of events with mark 1 actually can be given by independence of Poisson processes, because both of these events, okay, the x1t and x0t both are following Poisson distribution, but both are independent. So we can use this independence property of the Poisson process to calculate the probability of having j number of events with mark 0 and k number of events with mark 1. We know that the x of t is equal to x0 of t plus x1 of t. Okay, so both the events combined form the total number of events. Okay, so the probability of x0 of t is equal to j and x1 of t is equal to k is equal to probability that the total number of events x of t is equal to j plus k, okay, into the probability that x0 of t is equal to j such that total number of events is equal to j plus k. X of t is equal to j plus k. So to find the conditioned probability, okay, we will use the total number of events as j plus k. So the probability that x0 of t is equal to j, okay, and x1 of t is equal to k, it will be equal to probability that the total number of events x of t is equal to j plus k multiplied by probability that x0 of t, the mark 0 number of events, is equal to j such that the total number of events x of t is equal to j plus k. Okay, now putting the values using the Poisson distribution, we know that the probability that x of t is equal to j plus k is equal to, using this probability Poisson distribution, okay, it will be equal to lambda t raised to power j plus k e raised to power minus lambda t divided by j plus k whole factorial. Okay, and this part, the conditioned part, is equal to the probability that x0 of t is equal to j such that the total number of events is equal to j plus k. It will be equal to lambda t raised to the power j plus k into e raised to power minus lambda t sorry this will follow binomial distribution. So binomial distribution, we have p, q, p raised to the power j and q raised to the power k, something like this. Okay, so putting the values, we can say that here the p, it is equal to j plus k, total number of events is j plus k, and it will be equal to p raised to power j into 1 minus p raised to power k. Okay, so putting both the values. Okay, so up till now we have the probability of the number of events with mark 0 is equal to j, and number of events with mark 1 is equal to k. It will be equal to the probability that the total number of events are combination of these j and k's multiplied by the probability that the number of events with 0 mark is equal to j, such that the total number of events is equal to j plus k. Okay, so this is Poisson, this is also Poisson, but these are conditions, so it will follow the binomial distribution, and this is a purely Poisson. So the probability for the total number of events to be j plus k, it will be equal to e raised to power minus lambda t into lambda t raised to power j plus k divided by j plus k whole factorial. Okay, now let this is a and this is b part of this equation. Okay, so this represents the a. Okay, now for b, we have the probability that x naught of t is equal to j, conditioned on the total number of events is equal to j plus k. Okay, this follows the binomial distribution. Okay, and the p over here is equal to j plus k and q is equal to j, so it will be equal to j plus k combination of j p raised to power j and 1 minus p raised to power k. So writing this instead of b, we have the probability that mark 0 events is equal to j and mark 1 events is equal to k. It will be equal to e raised to power minus lambda t raised to power j plus k divided by j plus k whole factorial multiplied by j plus k combination of j p raised to power j into 1 minus p raised to power k. Okay, so finally what we get is, we get lambda t raised to power j plus k e raised to power minus lambda t p raised to power j into 1 minus p raised to power k divided by j factorial into k factorial. Okay, and how we get this is, we open this j plus k combination of j plus k combination of j is equal to j plus k whole factorial divided by j factorial into j plus k minus j whole factorial. So it will be equal to j plus k whole factorial divided by j factorial into k factorial. Okay, so this j plus k factorial, okay, it will be cancelled by this j plus k factorial. Okay, and we will only get j factorial into k factorial in the denominator. So that is how we get it. Okay, this was just for your understanding. I just opened this combination j plus k combination of j. Okay, the rest is same. So this is the final equation that we get for the marked Python process. Okay, and this represents if we have two types of events occurring over time period t, we can exclusively find the probability for each of the events to be occurring for the specific number. For example, we want to find for example, we have two kind of customers, okay, for biscuits and for cold drinks. Okay, so the probability that we are getting 3 number of customers for biscuits and 5 number of customers for the beverages, we can find the probability using this exact equation. Okay, I will use it in the example as well as in the problem 6.1 that you already mentioned to me that solve this. Okay, so I will use this specific formula in both of these sample question and the exercise question. Okay, you will find it useful. You can then use it in exam to find the solution of such problems which involve the marked Python processes. So continuing to the example first. Okay, I will be doing this example first, which is on the page 322. Okay, example on page 322 first, which is on the page 322. Okay, example on page 322 page. Okay, it says that the customers enter a store according to Python process of rate lambda is equal to 10 per hour. So the lambda or the rate is 10 per hour. Okay, these are the customers entering a store. Now independently each customer buys something with probability p is equal to 0.3. So the probability is 0.3 or 30%. There is 30% chance that the customer will buy something, okay, and leaves without making a purchase with a probability of q, which is equal to 1 minus p is equal to 1 minus 0.3 is equal to 0.7. Now remember this, we have divided the customers into two. Okay, the mark 0 and mark 1 over here will be the customers buying product, and its the probability will be p is equal to 0.3, and mark 1 will be the customers that do not buy anything, only come and leave without buying anything, and its probability is equal to q, and it will be equal to 0.7 or 70% chances. So this system tells us that two types of customers are entering into the shop. The first one is those customers which buy something, and its probability is 0.3%, 3 or 30% chances, and the customers which do not buy anything. Okay, so mark 0, for example, it represents the customers buying, and mark 1 represents the customers that are not interested in buying, they just come and go. Okay, we want to find the probability that during first hour 9 people enter the store, and 3 of these make the purchase and 6 don't make any purchase. Okay, so the x of t over here is 9, because we have 9 people that enter the store in the first hour. So x of t is 9 and x naught of t, the people which are buying upon entering are 3, x1 of t is equal to 6. Okay, so the probability that x naught is equal to 3 is equal to, it will just follow the Poisson process, okay, because both are independent of each other. So it will be equal to e raised to the power minus 3 into t, okay, and lambda t raised to the power 3 divided by 3 factorial. Now lambda over here, we know that lambda is equal to 10 and t is equal to 1 hour. Okay, so putting the values, we get e raised to the power minus 3 into 1 raised to the power 3 divided by 3 factorial. So it will become e raised to the power minus 3 and 3 cube, which is 9, and 3 factorial is equal to 3 into 2, which is 6. Okay, and it will give us 0.2240. So there are 22.4% chances that 3 customers are entering in the first hour which buy something. Okay, now we want to find x1 of t is equal to 6. Probability that x1 is equal to 6, it will be equal to e raised to the power minus lambda t raised to the power n divided by n factorial. Now n over here is 6. Okay, lambda is equal to 10 and t is equal to 1. So putting the values, we get e raised to the power minus 10 into 1 and 10 into 1 raised to the power 6 divided by 6 factorial. So it will be equal to e raised to the power minus 10 raised to the power 6 divided by 6 factorial. So sorry, one mistake that I made is that for each independent I did not calculate the independent rates. Okay, for example, for x naught of t, the rate will be equal to Poisson lambda t into p. Okay, so because we are not 100% sure that a person entering with the rate lambda will buy anything, so we need to multiply the probability with it. Okay, so it will follow the Poisson process with the rate of 10 into 1 into probability 0.3. So it will be equal to 3 per hour. Okay, x naught of t. And similarly x1 of t, it will follow the Poisson process of lambda t into q. Okay, and it will be equal to 10 into 1 into 0.7. So 7 per hour for the x1. So now I need to put these rates in here. Okay, so now the probability that x naught is equal to 3, it will be equal to e raised to the power minus lambda t raised to the power n divided by n factorial. Now lambda over here is this one updated, 3 per hour. Okay, for x naught. Okay, so it will be equal to e raised to the power minus 3 into 1, t is equal to 1 hour because we are only measuring it for 1 hour. So and it will be equal to 3 into 1 raised to power 3 divided by 3 factorial. So it will be equal to e raised to power minus 3 cube divided by 3 factorial, which is equal to 3 into 2 is equal to 6. Okay, so 9 e raised to power minus 3 divided by 6, it will be equal to 0.2240 or 22.4% chances that 3 people are entering in the store in the first hour and they are buying anything. Okay, now we need to calculate the probability that x1 is equal to 6. So it will be equal to e raised to power minus lambda t raised to power n divided by n factorial. Now n over here is 6. Okay, n is equal to 6, lambda is equal to this one, 7 per hour, and t is equal to 1 hour, because we are measuring it for only first hour. So probability that x1 is equal to 6, it will be equal to e raised to power minus lambda t, so minus 7 into 1, and it will be equal to 7 raised to power 6 divided by 6 factorial. It will be equal to 0.1490 or 14.9% chances that 6 people are entering in the store in the first hour and they are not buying anything. Okay, now the conditioned probability will be equal to the probability that x0 is equal to 3 and x1 is equal to 6. It will be equal because both are independent of each other, so we can just multiply it. Okay, so for the first, it will be equal to probability that x0 is equal to 3 multiplied by the probability that x1 is equal to 6. So we have already the values which are equal to 0.2240 multiplied by 0.1490. So it will give us 0.0334 or 3.34% chances. Okay, so there are only 3.34% chances that exactly 3 number of customers are buying anything and 6 number of customers are not buying anything. Okay, sorry for the mistake, because I took it for lambda is equal to 10, but here we have the probabilities given. So for that we need to multiply that rate with the probability to get it for exclusively for the x0 and x1. Other than that, the process is same. Thank you. Okay, so in this video we will be doing the exercise problem 6.1. okay, the page number is, let me see in the book, page number is 328. Okay, and this is the problem, okay, that we will be doing, the customers demanding services. Okay, so the question says that customers demanding services at a central processing facility arrive to a Poisson process of intensity theta is equal to 80 per unit time. Okay, so theta, okay, we can also write it as lambda in many cases, but here it is given as theta. So theta is equal to 8 per unit time. Okay, the unit time can be hour, it can be per minute, it can be per second, any time. Okay, so and t is equal to 1, okay, because it is per unit time. So it says that the facility the customers arrive at the rate of theta is equal to 8 per unit time. Okay, so now the rate of the process, okay, this is the Poisson process, so rate of the process is given to us. Second thing is, independently each customer is classified as high priority with probability alpha is equal to 0.2. okay, it means that we have 2 marks over here. Okay, x0 and x1. x0 means that the classification is of high priority customer. Okay, and x1 means with low priority. The probability over here, it is denoted by alpha. Earlier we denoted it with this sign, but here it is given using alpha, and alpha is equal to 0.2. It means that with each customer arriving, there is 20% chances that it is high priority customer, and on the contrary, for the low priority, the probability is 1 minus alpha, which is 1 minus 0.2, or 80% chances. Okay, so we have 80% chances that a customer arriving at this facility is low priority, and we have 20% chances that any customer that is arriving at the center is high priority. Okay, now they want us to find what is the probability. Okay, what is the probability that 3 high priority and 5 low priority customers arrive during the first unit of time. Okay, it means that at first hour or at first minute, whatever you consider it, we will do it like in hour. Okay, for our own so now solving this problem. Okay, so in this, the number of customers arriving, it follows the Poisson distribution with a rate of theta is equal to 8 per unit time. Okay, now the probability that x naught, okay, is equal to 3, it will follow the Poisson process. So it will be equal to e raised to power minus lambda t raised to the power n divided by n factorial. Now in this case, n is equal to 3 because we want to find it for 3 number of customers. Okay, and lambda over here, it is equal to 8 multiplied by the probability, which is 0.2. So lambda is equal to 8 into 0.2. Okay, so it will give us the exact probability for the high priority customers. Okay, so let's find out this lambda. Okay, so it will give us a rate of 1.6 customers per unit time. Okay, so lambda, or we can say lambda naught, or high priority rate is equal to 1.6 per unit hour. So now putting the values, we get e raised to power minus 1.6 into 1, because t is equal to 1, we are doing it for only 1 hour or 1 unit time. Okay, into 1.6 raised to the power n is equal to 3 divided by 3 factorial. Okay, so it will be equal to e raised to power minus 1.6 into 1.6 raised to the power 3 divided by 3 into 2 into 1. Okay, so it will give us a value of this 1.6 whole cube. It will give us a value of 4.1 approximately, multiplied by e raised to power minus 1.6 divided by 6. Okay, and so it will give us a value that is approximately equal to 0.202. okay, or 20.2% of chances that there are 3 customers arriving in the first hour which are high priority. Okay, now similarly doing it for the low priority. So the probability that x1, okay, because we have represented lambda 1, for this it should be found prior to processing this. Okay, so lambda 1 is equal to theta multiplied by the probability, which is 1 minus alpha. Okay, so theta is equal to 8 multiplied by 1 minus alpha is equal to 1 minus 0.2, or we can also write it as beta. Okay, and beta is equal to 1 minus alpha, and it is equal to 0.8. Okay, so 8 multiplied by 0.8, this is the rate for the low priority customers arriving per unit time or per hour. Okay, so calculating this, we get, when we multiply 8 with 0.8, we get 6.4. So the rate for x1 or the customers with low priority is 6.4 customers per hour or per unit time. Okay, now using the Poisson distribution, actually the probability that x1 is equal to 5, it is equal to e raised to power minus lambda t raised to power n divided by n factorial. Okay, now here n is equal to 5, lambda is equal to 6.4, and t is equal to 1. Okay, so doing this, we get the probability for the low priority customer is equal to 5 in the first hour. It is equal to e raised to power minus 6.4 into 6.4 raised to the power 5 divided by 5 factorial. Okay, so it will be equal to e raised to power minus 6.4 multiplied by, now 6.4 multiplied raised to the power 5, it will give us roundabout, let me calculate it, it will give us 6.4 raised to the power 5 is equal to, this gives us 1074. Okay, so it is equal to 1074 divided by 5 factorial. So 5 factorial will give us 120. Okay, so calculating this, it will give us an exact value of 6.4, because e raised to power minus 6.4, it is equal to this factor, actually this one, it is equal to 0. I must write it over here, e raised to power minus 6.4 is equal to 0.0016. Okay, so putting the values, we get 0.0016 multiplied by 1074 divided by 120. Okay, and it is equal to the probability that the low priority customers are 5 arriving in the first hour. So the probability that the low priority customers are 5 in the first hour, it is equal to 0.0016 multiplied by 1074 whole divided by 120. So simplifying this, it will give us a value of around 0.01485. So roundabout, it will give us 0.15 or 1.5% chances. Okay, so there are only 1.5% chances that there are 5 low priority customers coming in the first hour. I made a mistake prior to this, because this value this is the value of e raised to power minus 1.6. okay, this is the value of this. So putting the values, we get 0.202 multiplied by 4.1 divided by 6. Okay, so it will give us a value of 0.1377 or 13.77% chances. Okay, so there are 13.77% chances that in the first hour we get 3 high priority customers, and there are 1.5% chances that we get 5 low priority customers. Okay, now these both are kind of happening in the same time frame. Okay, so both are independent of each other. So the probability that we have 3 number of customers in the first hour and 5 number of customers with the low priority in the first hour, it will be equal to combined, it will be equal to the probability that we have x0 is equal to 3 multiplied by probability that we have x1 is equal to 5. Why we multiplied it directly? Because both are independent of each other. This is the quality, this is the kind of characteristic of this marked Poisson process, that both marks are independent of each other. Both marks are independent and identically distributed. So we just multiplied it plainly. Okay, we find the probability independently and then multiply it. So for this we have a probability of 0.1377 multiplied by 0.015. So combined we have a probability of around, this multiplication will give us a value of 0.00204 or 2.04% chances that we have exactly 3 high priority customers and 5 low priority customers in the first hour or first unit of time. So this is how we solve questions based on the marked Poisson process. In this video we will be doing the exercise problem 6.3. Okay, so the question says that let n of t, which is the total number of events at for certain time t, such that t is greater than or equal to 0. It means that we have some time period, follows Poisson process. It is Poisson process with the rate or intensity of lambda. Okay, so here it is given to us that the number of events occurring over time t, it follows the Poisson distribution and its rate is lambda. Okay, so this is the first thing that is given to us. The next thing is that y1, y2 be independent and identically distributed non-negative random variables with cumulative distribution function of g of y is equal to probability that capital Y is less than or equal to y. Okay, so if we consider the compound Poisson process, okay, what we had, we had y1, y2 up to yn. Actually these were identically and distributed and independent random variables. Okay, and these represented shocks or damages that accumulated over the time period t. Okay, so if there was a shock happening, okay, at w1, it has some intensity of y1. Here y2 y3, y4 and so on. So it was making a graph like this. So these y1, y2, y3, y4, these are the independent and identical distributed random variables, and what it shows is, it shows the shocks or the damage that has been done at each interval of time or at each event happening. W1 is the waiting time for this event to happen, and Y1 is the damage that has been done due to this event occurring at W1. Similarly, Y2, Y3 and Y4 and so on. So Y1, Y2, Y3, these are the identical distributed and independent random variables. Okay, so this thing is given to us. The third thing that is given to us is that these IIDs have a CDF or cumulative distribution function, which is represented by G of phi, capital G of phi, and it is equal to the probability that the capital Y, okay, capital Y is the sum of these damages is less than or equal to small y. Small y is the critical level of these damages. Okay, now what you want to find is, you want to determine the probability that Z of t, which is the cumulative damages, is greater than Z is the critical level, based on or conditioned on the number of events, total events, is greater than 0. This we need to find out. Okay, so let's solve this problem. So we know that the total events, it follows Poisson distribution with the rate of lambda t. T I am writing because we have certain time period and the overall rate is lambda. So whenever we have a time period given, the rate changes with this specific time period. Okay, for example, we have a rate of 8 per hour, for example, and the time of consideration is 2 hours. So then the rate is equal to 8 into 2 is equal to 16 per time period. So for overall time period the rate is 16, but for unit time the rate is 8. So that is why we write lambda t. If you don't write lambda t, we can also write only lambda, just like I wrote over here. So it is not a problem. This is for just your understanding. Okay, so now we know that the probability, now this is conditioned. Okay, this is the overall damage greater than critical level Z, conditioned on the number of events greater than 0. So whenever this condition happens, actually now we have the formula like this. Okay, the probability that Z of t is greater than Z such that the total number of events is greater than 0, so it will be equal to probability that the overall damage is greater than critical level Z, okay, and number of events greater than 0 divided by probability that number of events is greater than 0. Okay, remember that we have and over here. Okay, we have both these probabilities. Now splitting the numerator, the probability that this is denoted as A. Okay, we are going to find the numerator and denominator and put it in A to find this exact question that is asked in the exercise problem 6.3. Okay, so now we must decode the numerator part. So we can write the probability, and the time of consideration is 2 hours. So then the rate is equal to 8 into 2 is equal to 16 per time period. So for overall time period the rate is 16, but for unit time the rate is 8. So that is why we write lambda t. If you don't write lambda t, we can also write only lambda, just like I wrote over here. So it is not a problem. This is for just your understanding. Okay, so now we know that the probability, now this is conditioned. Okay, this is the overall damage greater than critical level Z conditioned on the number of events greater than 0. So whenever this condition happens, actually now we have the formula like this. Okay, the probability that Z of t is greater than Z such that the total number of events is greater than 0, so it will be equal to probability that the overall damage is greater than critical level Z, okay, and number of events greater than 0 divided by probability that number of events is greater than 0. Okay, remember that we have and over here. Okay, we have both these probabilities. Now splitting the numerator, the probability that this is denoted as A. Okay, we are going to find the numerator and denominator and put it in A to find this exact question that is asked in the exercise problem 6.3. Okay, so now we must decode the numerator part. So we can write the probability that Z of t is greater than Z and n of t greater than 0, it is equal to, if we have and over here. Okay, so what we can do is we will find the probability that the overall damage is greater than Z conditioned on number of events is equal to n multiplied by the probability that number of events is equal to n. Okay, so let's write it as for example 1. Okay, so put 1 in A. Okay, this is the numerator part, so putting this output in this A, so we get probability that Z of t is greater than Z such that number of events are greater than 0. It will be equal to probability that Z of t is greater than Z such that n of t is equal to n multiplied by probability that n of t is equal to n divided by probability that n of t is greater than 0. Okay, so what we did is we just explored the numerator part and put the answer into the A, this A equation. Okay, so now I will find the probability for this part, and the third part individually and then put it in A, so we get the final equation. Okay, so first explore this one part, this is second and this is third. So for 1, okay, or part A, this one, probability that Z of t is greater than Z such that n of t is equal to n, it is equal to (1 minus g of z raised to the power n. Okay, so how we actually came to the conclusion that it is equal to this thing? From the compound Poisson process, we know that probability of the overall damage is less than or equal to certain level z, such that n of t is equal to n. It is equal to g of z raised to power n. Okay, so this is less than or equal to, so when it converts into greater than or equal to, so it will be equal to 1 minus this thing. Okay, or like I can explain it as like when we toss a coin actually, so there are two possible outputs, okay, head and tail. So for example, the probability for head P is 0.3. So what will be the probability for tail? It will be equal to 1 minus this probability, 0.3. Okay, so similarly, if the probability for z of t is less than z, such that n of t is equal to n is equal to g of z raised to power n, then the probability for z of t greater than z, it will be equal to 1 minus this thing. Okay, I will continue this in the next video. So continuing the same problem, up till now we found that the probability that the overall damage is greater than z, such that total number of events is equal to certain level n, it is equal to 1 minus g of z raised to power n. Okay, now we have the second part of the equation A. So for part 2, the probability that number of total events is equal to n, it will be equal to, using the Poisson process, it will be equal to minus e raised to power minus lambda t raised to power n divided by n factorial. Okay, but we have another thing, which is the denominator. The denominator is this thing, probability that number of total events is greater than 0. So for 3, which is probability that the number of total event is greater than 0, so it is equal to 1 minus probability that number of events is equal to 0. Same like I did the example for the head and tail. So the probability that number of events is greater than 0, it will be equal to 1 minus the probability that number of events is equal to 0. So it will be equal to 1 minus this, using the same formula. Okay, so here n is equal to 0 over here. So putting n is equal to 0, we get e raised to power minus lambda t only. Okay, because lambda t raised to power 0, it will become 1, and 0 factorial is also 1. So we will be left with only e raised to power minus lambda t. So we will get 1 minus e raised to power minus lambda t for this thing, probability of n of t greater than 0. Okay, now putting 1, 2 and 3 in A. Okay, so what was A? The A is this thing, probability that total damage is greater than z, such that n of t is greater than 0. So it was equal to probability that z of t is greater than z, such that n of t is greater than 0, divided by probability that n of t is greater than 0. So we explored the numerator part, and we came to the conclusion that it is equal to the probability that z of t is greater than z, such that n of t is equal to n multiplied by probability that n of t is equal to n. So now putting the value, I will write the equation over here, the A equation over here, and then put these 1, 2, 3, okay, so that you understand. So the probability that z of t is greater than z such that n of t is greater than 0, it will be equal to probability that z of t is greater than z such that n of t is equal to n multiplied by probability that n of t is equal to n divided by probability that n of t is greater than 0. So for the first one we have 1 minus g of z raised to the power n, okay, multiplied by, for the second part we have this e raised to the power minus lambda t raised to the power n divided by n factorial, and in the denominator part we have 1 minus e raised to the power minus lambda t. Okay, so here we get e raised to the power minus lambda t into lambda t into 1 minus g of z raised to the power n divided by 1 minus e raised to the power minus lambda t. Okay, and this is the required equation, okay, for the probability that the overall damage is greater than z such that the total number of events is greater than 0. So this is the required equation. Okay, I hope you find it useful and you understand the process. Thank you.